Okay, so I think let us start and let us try to end polynomial chaos expansion to the extent possible. My guess is that it will not be completed today. We will need one more lecture, but it will definitely be completed by tomorrow. And because I want to complete it by tomorrow, there are things that I'm going to skip today. I'm just going to tell you, but not prove them. But then you can learn those prove on your own because those are from numerical methods, quadrature and all those things that I was talking about, right? So the plan for today is that we will discuss quadrature, at least 3-4 types of quadrature, quadrature in 1D, quadrature in 2D, and wrap up discussion on quadrature. And then given time permits, we'll start talking about polynomial chaos expansion in action for uncertainty quantification and more so for reliability analysis. Okay. So we were talking about, in the last two lectures, if you remember, we talked about different spaces, Hilbert space, Banach space, and all those things. In the Hilbert space, we talked about how to compute inner product and how to formulate orthogonal basis and orthonormal basis, and then how any point on the Hilbert space can be represented as a linear combination of orthonormal basis. And we discussed that. And I told you that that is nothing but the polynomial chaos expansion. I don't know the name chaos came from where, but that is essentially the polynomial chaos expansion. And that is what we discussed last time. But then one essential part in polynomial chaos expansion is to compute the inner product. And computing the inner product means computing the integration. And in most cases, those integration you will not be able to compute them analytically. Not all functions are analytically integrable. And so we will have to use some numerical technique. And numerical technique that we use for approximated integration is quadrature, right? So that was basically where we stopped last time, right? That is where we fundamentally stopped last time. Okay. So let us start from that point. So in polynomial chaos expansion, we have to deal with inner products, right? We don't have an option and we have to deal with inner products, and these inner products are essentially integrals. So these are essentially integrals, right? And to compute this integral, we use quadrature rule or quadrature method. And these integrals in most cases are computed using quadrature. Okay. And that is why we are going to talk about quadrature majorly in today's lecture, right? So let us go to quadrature. Let us go to quadrature. And in quadrature, let's take a generic integral, because quadrature are for solving integral. Let us keep it simple, forget about PDFs, and let's talk about integrating a function fx in some range a to b. Okay. So we want to evaluate this integral I, which is integration a to b fx dx. Okay. Now, although I am saying that forget about PDFs, there is a PDF here. It's a uniform PDF that is sitting there, which is a constant. So that is outside the integral. I don't care about it. So I'm not writing it. So even when I say there is no PDF, there is always a PDF, and that PDF in this case is the uniform PDF, a constant PDF, right? So it is still there when I'm saying, but you can imagine if the PDF is there, you can still do this, right? Now in quadrature rule, can someone tell me how do we approximate this I? Generic quadrature rule. What do we do? We can convert this integral into summation, and then I have something known as nodes or quadrature points. We evaluate the function at the quadrature points, and each of these quadrature point evaluated function has a weight, similar to importance sampling, similar to Monte Carlo integration. All of those you can think of it as quadrature rule. In Monte Carlo integration or Monte Carlo simulation, the vanilla version, you know that it's a quadrature rule where the nodes are sampled randomly and all the nodes are equal weightage 1 by n, right? In importance sampling, you know that it is sampled from some importance sampling density, and the weights are importance sampling weights, which is the ratio of the PDFs, right? Evaluated at that point. And so all of those, right? But today, and those are, by the way, stochastic rules. Those are, we don't call them quadrature because those are stochastic in nature. Every time you do it, you get separate result. Quadrature are deterministic in nature. Every time you solve it, you should get the same result. In MCS, in importance sampling, you will not get. And that's why people do not call them quadrature rule. But essentially, if you think about it carefully, it is similar to quadrature rule. Okay. But just that it's a stochastic thing. It's not a deterministic thing. Right? Okay. So quadrature. This is we approximate I as I approximately equal to I hat is equal to summation I equal to 1 to n cube Wi if xi. Okay. What is NQ? Number of quadrature points, right? What is xi? The nodes or the quadrature points. What is Wi? The quadrature weights, right? So this is my nodes, or also called known as quadrature points. This is my quadrature weights, or I'm going to write only as weights, and this is my number of quadrature points. And the idea is that as you increase the number of quadrature points, your estimate should be more and more accurate, right? That's the whole idea of any quadrature rule, that it should be a convergent kind of thing. As you increase the number of points, it should converge, right? Now, last time I was telling very quickly, right? Let us talk about some quadrature rule. This is the generic one. The most easiest one is the midpoint rule, right? So, example 1, midpoint rule. So, suppose I have a function like this, okay, randomly I am drawing it, right? Some function f, and I want to integrate it in the range. So, I want to integrate it in the range. This is my a, this is my b, okay, and I want to integrate it in this range. This function may not be known to me, it may be very complex and all those things, but this is the function I want to integrate. The midpoint rule says the following thing. In midpoint rule, as the name suggests, you have one node and that node is the midpoint, okay. So, you have one node and that node is the midpoint. So, this is my x1, which is equal to a plus b by 2, right? and at the node I evaluate f. So that is my this point. This is my f of xi or x1 in this case. And then I approximate the area under the violet curve by the area under the red curve. I approximate the area under the violet curve by the area under the red curve, and that is my quadrature rule. In this case, that is my midpoint. Okay. So in this case, my I hat is equal to b minus a, that is the length, multiplied by f evaluated at x1, which is a plus b by 2, right? What is my node here? A plus b by 2 is my node. What is my weight? B minus a is the weight. There is no summation because there is only one node. That's why it's the midpoint rule, right? You can understand this will not work in most cases until and unless a and b are very close to one another. If a and b are very close to one another, then this is fine. Otherwise, it will not work. B minus a is weight. No, b minus a. See here. What is weight? Whatever is getting multiplied with f of xi. So what is getting multiplied with f of xi? B minus a. Right? Okay. Okay. So this is the simplest possible rule. I mean, no one calls it quadrature rule, but it's a quadrature rule. Okay. Because when you hear the term quadrature, by default your mind goes to Gauss quadrature and those kind of things. We'll go there, but everything, trapezoidal rule also, that's the next thing I'm going to discuss, but you don't call them quadrature rule, but those are quadrature rules. Okay. So next thing is trapezoidal. Trapezoidal rule. Okay. What do you do in trapezoidal rule? Let's take another color. In the same diagram I'm going to draw. Okay. In trapezoidal rule, what you are going to do is that you have two nodes. What are the nodes? The first point and the last point. So this is your first point, this is your last point. And then, so basically your x1 is equal to a, x2 is equal to b. So you end up with two nodes. Now what do you do? How do you approximate? The name itself has it. The area under the green curve will now act as an approximate, right? That is an approximate to the area under the violet curve, right? So in this case, what is my I hat? Half b minus a multiplied by the f at a and plus f at b, right? A plus f at b, right? This is the area. Again, b minus a by 2 is your weight, and both the points are getting the same weight. The two nodes are fa and fb, so a and b are your two nodes, two quadrature points, right? Again, it will not work until and unless both are very close by, or your function is some linear function. Then it is fine, right? So now moving ahead, these are very simple ones. So let us make it a little bit complex. Why should there be only two nodes, right? So let's move to the third one, and this is basically known as Newton-Cotes quadrature. Cotes quadrature. Okay. By the way, one or two quadrature I will not write because then I will not be able to start PCE today. So I will go to slide. Okay. And also I need to show some diagrams specifically in some advanced quadrature. So there I will use the slides. Okay. Okay. Newton-Cotes. You know what is Newton codes? Have you studied it? MTL 107 might have, I think. No? Anyways, I'll anyways cover it. So here what you do is that this is kind of gives you more flexibility. You can decide the number of quadrature points now. In the previous two cases, it was fixed 1 and 2. In this case, you decide the number of quadrature points. And whatever you decide, you divide the interval equally in that limit. Okay. So step 1 is select NQ and divide the interval, and the key point is equally or equidistance, distant, whatever you call it. Okay, so that means each interval will be of equidistant. So you will get NQ points, NQ minus 1 intervals, or NQ plus 1 points, NQ intervals, whatever you take it, right? But they are equidistant, and that is important. Next, what you are going to do is that the next thing you do is you fit a Lagrange's polynomial through these Q points. Fit a Lagrange's polynomial passing through the NQ points. Everyone knows what is Lagrange's polynomial? For n points, you get a n minus 1 order polynomial. You found the Lagrange's coefficients and multiplied with the polynomial, right? So the Lagrange's is x minus x1 multiplied by x minus x2 multiplied by x minus x3 dot 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 divided by x1 minus x2 multiplied by x1 minus x3, and that gives you basically the first one. So if you don't know, please read about it. I'm sure you have studied it somewhere. FEM, the first thing that is done is Lagrange's interpolation. It's very common. Read about it because it will be needed. Okay, but the point is that you basically fit a Lagrange's polynomial, and this polynomial that you get is now a representative of the actual function f. This Lagrange's polynomial is now representative of the actual function f. So what you will do is that now you will integrate from a to b this Lagrange's polynomial, and you will do it as a summation, so you will get it. So you fit a Lagrange's polynomial, and then area under the Lagrange's polynomial is equal to I hat. Okay. So this is basically what you, and if you rewrite it, you will see that you are getting NQ weights and NQ nodes. NQ nodes to anyways you are getting, and if you write this Lagrange's polynomial, put it and do it, you will see that you will get some weights that will come for each of this point. But this is a very bad scheme. Any idea why? One reason obviously is Lagrange's polynomial. It overfits, or to be very honest, it is very, overfitting is still okay, but it is very bad in extrapolation. So what will happen is that if you go beyond b, it will go to plus infinite or minus infinite. If you go before a, it will again go to plus infinite or minus infinite. I mean, these polynomials are very ill posed in nature, specifically when the points are equidistant. Specifically when the points are equidistant. Okay. And because of this phenomena, what you observe is known as the Gibbs phenomena. Anyone knows what is Gibbs phenomena? Have you heard the term? Okay, I'll explain it. You know? Gibbs phenomena. It has nothing to do with that. Suppose I want to approximate a step function. Okay. And let's think about sinusoids, just as an example, because that's very prominent Fourier series. What do you think will happen if I use 100 terms in the Fourier series? How will you get it? How will it look? If you use 100, which is quite large, right? It will look something like this. Right? This portion you see, this kind of sudden jump, this is known as Gibbs phenomena. So now you can imagine if you fit a Lagrange's polynomial with this number of points to this function only, you will get something similar. Even if you take 1000 points, you will see that it will gives you Gibbs phenomena. What kind of polynomial will you get with Lagrange's? It will be even worse. With Lagrange's, if you have too many points, you will get something like this. Something I don't even know. And after this, you will go to infinite. It will go to. So Gibbs phenomenon is very prominent, specifically when the points are equidistant. Because those points are not adaptive. It does not know what curve you are doing, what you are doing. It knows nothing. As a result, it happens. It will be much better if you select the points judiciously, and in that case, you will probably get a I hat or F hat, which will still have Gibbs phenomena, but it will be minimized. So this Gibbs phenomena is a well-known phenomena that is shown in Fourier series and obviously Lagrange's polynomial as well. And because of this Gibbs phenomena, the area you get is wrong. Okay. What will happen is this portion will start dominating your area. Okay, and so you will get something totally useless. Okay, you will get something that is not at all useful. Okay, yeah. So this is not that popular because, or rather, Newton codes suffers from Gibbs phenomena. How is it? How can you solve it? By selecting better point, right? How do you select the point? Now all of you know about Gauss quadrature. Gauss quadrature is what is an improvement over this. So in Gauss quadrature, how do you get the quadrature points? Any idea? I know the points are given to you, these are the points you are supposed to use, but have you ever asked how do you get those points? The quadrature points. All of you know about Gauss quadrature, right? In FEM you have done it, so.
Check their knowledge, point.
Yeah, how do you get in Gauss those points? Chebyshev you get by something else, but anyways, in Gauss quadrature, the original Gauss quadrature, how did Gauss came up with those points? Those points are the roots of the orthogonal polynomial. So the Gauss quadrature points, so orthogonal polynomial has many applications. This is another application. So suppose you are working in the standard Gaussian space, right? So you will use Hermite polynomial, that is the orthogonal polynomial. So now the roots of the Hermite polynomial. So suppose now you want to use n collocation points. You will take the nth order Hermite polynomial and find the roots where it is going to 0. Those will be your quadrature point. Okay. And once you get those points, then it's exactly same as the Newton codes. You fit a Lagrange's polynomial and do the exact same thing. Okay. Then it's exactly the same thing. The points you get from the roots of the nth order orthogonal polynomial, and that will give you n. So nth order orthogonal polynomial if you want nq quadrature points. So Gauss quadrature now I have to jump. Okay, improves this. Okay, by selecting better nodes. Gauss quadrature improves the Newton codes method by selecting better nodes. How will you select better nodes? As I said, the nodes are selected to be the root of the orthogonal polynomial. roots of orthogonal polynomial, and remaining steps remain the same. You don't change the remaining steps. This is the only step that you change, and then it's same. And this is why is Gauss quadrature so popular? Any idea? There must be some reason, right? What does it mean? I mean, everything is approximately real function. Newton course is approximately real function. MCS is approximately real function. What is approximating imaginary function? Nothing, right? You are in the right direction, but the numbers are wrong. So you can show, and I'm not going to show, but there is a theorem that proves that in Gauss quadrature, with nq points, you can get exact approximation for 2nq plus 1 order polynomial, and which is outstanding. With n points, n quadrature points, it can exactly approximate. It is like an universal approximator for polynomials having order 2n plus 1. And that is why when you do finite element, you use very few quadrature points, right? 3, 5, that's because with 3 it is actually approximating 7. So that is why quadrature is preferred, because you are doing that. Okay. And you can also show, and that's another theorem, that no other quadrature method can beat Gauss quadrature when it comes to polynomials. Okay. But these two theorems means nothing when your actual function is not a polynomial function. If your actual polynomial is a sinusoid, that's an infinite dimensional polynomial. So for an infinite dimensional polynomial, this will mean nothing. You might have better approximations, okay? But this is popular because of this reason, okay? No, I did not prove. I only said that you can imagine, I mean from intuition, right, that if I put the points, let's say where the gradient is high or something like that, in that case the phenomena will be less. So I did not prove it. It can be proven. And similarly, these two theorems also I am not proving it. I am just stating it, that Gauss quadrature with n quadrature point can exactly approximate polynomial of 2n plus 1 order. And for polynomial functions, no method will give you better approximation than Gauss quadrature. But even after that, we are not going to use it. Why? We are not going to use it because the quadrature points that we get in Gauss quadrature are not nested. What do I mean when I say not nested? Any idea? Correct. Suppose I am selecting n minus 1 points or n points. Next time I am selecting 2n points. There will be nothing common between this n and 2n. You have to again evaluate this function at 2n new points. So that means it is not nested. So as you increase the number of points, the previous points you cannot reuse. And because you cannot reuse, and in an ideal case you will not know what is the number of points you should use, so you will go sequentially, right, increasing points. And because you cannot reuse, you have to every time do calculation from scratch, right? That is the reason that this happens. Like in Newton codes, for example, it's nested. Equidistance, right? N and 2n you go, you will use the same points, you can understand, right? So Newton's actually is nested, but it's not good because of some other reason. This one is not nested, and as a result you cannot reuse the points again and again, and because you cannot reuse, that's a quality we do not want. That's a big no for us. So that's why this is not used in our app, in this kind of app. We use it in finite element where we don't do in nested manner. We don't keep on increasing the quadrature points, right? So that's why you use it in finite element. That's fine. So it has lots of application. Unfortunately, this is not one of those. And this nested thing will become important when you go to higher dimension even more. Okay. So go.
Method gives us good results because of the modes that we've chosen.
Because of the orthogonal polynomial. Because of the orthogonal polynomial, because nodes are function of orthogonal polynomial, and orthogonal polynomial gives the best convergence in the Hilbert space. So because of that, it is happening.
If it is also the orthogonal, why I need to again and again in the case of nested to reduce.
Okay, good question. So let me. So suppose think of a nth other orthogonal polynomial. Now you want 2n points. What will you use? You will use a 2nth other polynomial, right? Are these two polynomials same? Will they share roots? Right? They will not share roots. So you then have to select polynomials that share roots. That when I go to 2n, n roots would be the same as the previous roots.
So for every psi value, I have to find this.
Let's not go to polynomial chaos right now. Let's just talk about quadrature. Polynomial chaos, where will it be used? You don't even know yet. You don't know where quadrature I am going to use in polynomial chaos. So I have not reached that point. But think of it like that, that number of function evolution f will be again have to be restarted for each time you change the order or the number of n cube. Let's understand until that point. How it will be used in polynomial chaos is what I want to discuss today. And I don't have much time, so let's go to the slide next, okay? So this is not nested, right? The nested one is known as CC quadrature. Clenson and the other C I forgot the name. Last time also I said I forgot. So let's go there. Oh, I came to the right slide. So Clenso-Curtis quadrature. Okay, it is from here. So what it does? Don't read the whole thing; it will not make sense. There are a lot of things. What are we trying to approximate? Integration of fx dx. In this case, let us assume we are trying to approximate integration of fx dx in 0 to 1. 0 to 1 is the important point, keep that in mind. So that means if it is not 0 to 1, you have to transform it and bring it from 0 to 1. So we are trying to find out I, which goes from 0 to 1 fx dx. Okay. Now what we do is that we do a variable transformation. We assume x to be cos theta. Okay. If I assume x to be cos theta, dx will be minus sin theta d theta, right? And the limit will be pi to 0. So because of negative sign, I will make it 0 to pi. And when I make it 0 to pi, you end up with what I have shown in the below, right? Integration 0 to pi cos f of cos theta, that is f of x, and then sin theta d theta, that is your dx. Essentially, that is your dx, right? Clear? Now we want to approximate, instead of integration of fx dx, we want to approximate integration of f cos theta sin theta d theta from 0 to pi. Okay. Until this point, it is fine. Any question until this point? Because I have a tendency when I show slide, I go faster. So I will repeat things so that I don't go faster. That's why I don't use slide. Okay. So this portion is clear for everyone what we are doing. Now there is a f of cos theta sitting here, right? F of cos theta, we are going to write it in terms of Fourier series. Everyone knows Fourier series. A naught plus summation of cos plus summation of sine, right? The summation of sine you don't see in the Fourier series, right? Because f of cos theta is a even function. Cos of minus theta will become cos theta. So because of that, things will get cancelled out. You can write it down and you will find it out. Okay. So this is basically the Fourier series of f of cos theta. Right? This is the Fourier series, the series expansion of f of cos theta. You know the expression a naught plus summation I equal to 1 to infinite cos k theta, where k goes from, or cos I theta plus summation I equal to 1 to infinite sin I theta, something like that, right? You can always write that, and you can see that for f of cos theta, because it's an even function, signs will cancel out. Okay. Okay. Now you look at this expression here. I am going to substitute it here and then solve the integration. Clear what I am saying? I am going to substitute it here and solve the integration. What will I get? See, the first term I will get is a naught by 2 sine theta d theta from 0 to pi. Then that will become, Rakesh. So the first term will be a naught by 2 sine theta d theta, right? If I do an integration, sine theta will become minus cos theta. Now you put it there, you will see that it will end up, you will get 2 because pi and 0 will give 1 minus minus 1. 2 and 2 will cancel out and you will end up with a naught. Similarly, the other terms you can do cos theta, sine theta, you will find. So that will be sine a plus b plus sine a minus b. Now do the integration, half will come outside and you will end up with this term. Okay. So this integration gives you this summation form. What is unknown in this summation? Otherwise, this is my answer. A naught, a k. Basically, all the a's are unknown. In Fourier series, how do you find out a? You remember? A naught is integration of the function itself, and 1 by t, if it is going from 0 to t, 1 by t integration of the function dx. And what is the ak? 2 by the limit, so 2 by pi in this case, integration of the convolution, f multiplied by cos element d theta, which is this one. So this is your true function. Your convolution is with respect to cos k theta because you are trying to find out k. And then 2 by pi because the limit is from 0 to pi. So that 1 by t, 2 by t it becomes. And then d theta. This is supposed to give you your a of k. So by using this you can find out all the a's. If you find out all the a's, you will do this summation and that will give you the integration. And this integration is exact, by the way. This is exact. I have not done any approximations, right? So I will do some approximation, it's obvious. And that approximation will come in the integration that you see here, this integration. So this is to be approximated. This integration you cannot compute analytically in many cases because f of cos theta is sitting. So this is to be approximated. Not approximate, but approximated. And I'll recommend you read about this Nyquist-Shannon sampling theorem. This is from signal processing actually, because Fourier series. Using the Nyquist-Shannon sampling theory, this comes out to be this one. Again, this is exact if you for nq points. So if you increase the nq points, this keeps on increasing. So this gives you your ak. This is, yeah. Sure. Minus 1 to 1. Which one? Yeah. Correct. True. You are right. Let me correct it, right? Yeah, otherwise it will be pi to pi or something like that. Correct, thank you. Okay, and in fact that is why the signs will cancel out. I told the signs will cancel out because of that only, because the negative and positive sign will come, right? Okay, so when you use this and study about it, I am not going to go to this Nyquist-Shannon sampling theorem. That basically gives you this formula. There is a 5-page derivation that you can do, okay, or you don't need to do, to be very honest, okay. Because you are going to just use it. The main thing is polynomial chaos and I want to go there, so I am showing you this. But anyways, once you have this expression of ak, you can take this ak and substitute it into this expression, right? And that will give you an approximation for the integration from -1 to +1, right? So I will repeat it once more because there is too much information. So I am trying to approximate a function from -1 to +1. If the function is not in the range -1 to +1, we will transform it and make it in from -1 to +1, and that is easy. Okay. Now I will take the function from normal space to the cos space or theta space. Okay. In the theta space, I will represent a function using the Fourier series, and with the Fourier series, when you substitute that Fourier series into the expression, you end up with the expression that I have shown here in the last equation. This much is clear or not? I will repeat once more. I wanted to evaluate a function from -1 to +1, I integral of a function. I transformed x to theta by assuming x equal to cos theta, and then it gives me f of cos theta sin theta. F of cos theta, I do a Fourier series which gives me a0 by 2 plus summation of cos. This Fourier series expansion I go back and put into the integration and solve the integration, that gives me the expression at the bottom. Clear until this point? Forget about the what is after that. But now this expression I cannot use because a is unknown. To find out a, we know from Fourier series it's an integral, right? It's an integral, and that is the integral, and you can do that integral, correct? But we are not going to do that integral because it might not be possible. F of cos theta, f itself might not be known, so forget about f of cos theta. You can only evaluate f, but f might not be known in closed form, so you cannot solve that integral in that case. So what we do, we represent that integral using summation, and because it is Fourier series, we use the Nyquist-Shannon sampling theorem, which gives me this expression, this long expression that you see. So this expression is now my AK, and this AK, if I go and substitute into this, I will get my approximate integral, that, and then if you rearrange it, you will get summation of Wi Fi or f of xi. So you take this expression, substitute it into here, and then rearrange it, you will end up with the original quadrature formula, which is the generic one, summation I equal to 1 to nq Wi f of xi. Clear? So if this is clear, tell me what is xi in this case. Node I know, but what is xi? It's written actually. So for using the Shannon or the Nyquist-Shannon sampling theorem, right? You will select some nq points to represent this integral. Those points are your nodes. Okay? And those nodes are, you can see they are equidistant. J pi by nq. So j 1, 2, 3 will keep on putting j value, and it will be equidistant in that sense. I mean,
is theta value or
I mean, this is theta actually. Okay, this is actually theta j. This is theta. So what I'm trying to say is, you are right, this will be theta. So what I'm trying to say is that it is equidistant in the theta space. In the x space, it is not equidistant. I mean, that's what I wanted to say. In the theta space, you will end up with equidistant point. But when you go back into the x space, it's not. It's some random point. Okay. And this is basically what CC quadrature is. This is what the chainsaw-Curtis quadrature is. Let me repeat one more time. So you have a function that you want to integrate from -1 to +1. You will transform that into theta space by assuming x is equal to cos theta. The integration will change. F of cos theta you will write in terms of Fourier series. Substitute that into the integral, you will get a summation. What is unknown is a. A actually is not unknown, we know it from Fourier series. But that is also an integral that you might not be able to find out exactly. Now because we are in the Fourier series kind of expression, that is this Nyquist-Shannon sampling theorem, we use that. That gives me AK in a summation form. That I take and substitute into the original expression that I derived earlier. That gives me my quadrature rule. Okay. Now when I say it is nested, that is not true actually. It is nested when I go from n to 2n. If I go from n to n plus 1, it's not nested. So it is nested from n if I go to 2n or nq to 2nq. Then the previous nq are still there. So you have to only evaluate at nq new points. But if you go from nq to nq plus 1, then it's not. So that means here we will always go by a factor. So if I still take NQ points, then 2 NQ, so first 2 points, then 4 points, then 6 points, then I'll keep on doing it as a factor. N, 2n, 3n, 4n. I cannot take n plus 1, n plus 2. Then it is not nested.
In the Venn diagram.
I'll show you. I'll show.
Original equation that is also
That's what we're using. AK. But AK we are substituting here. AK is not my result. My result is when I substitute AK into this expression. I mean, that integration you cannot find out. That's the whole point. That you have done exactly. This is the exact expression of that. That's what we have find out here. This expression is not approximate. This is you take this, substitute it here, do it analytically. That's what I have shown here. So what you are saying is this one, right? Already done. Nyquist sampling you can only use when there is a specific form. Okay. And that form is, yeah, this 2 by pi has to be outside and all those things has to be there. So all those things are there. Okay. Read about that sampling. Okay. It's generally not covered in MTL 107. I don't expect you to know this. If you have done a signal processing course which goes into details of Fourier series, Fourier transform, wavelet transform, there you will find this. Okay. Okay. So yeah, this is nested only when we. So you were saying that how is it nested, right? A diagram. Or what does nested means? So nested means, let us take 2 space, and I'm only going to sample in this one. So suppose first I take 2 points. I mean 2 segments. So these are my 3, right? If at the next level my samples comes this, then I will call it nested because I'm reusing these things. But if the next step the sample comes to be, then it's not nested because I have to again evaluate all those points F. So nested means whatever samples you generated previously becomes a subset of the sample you are now generating at the current step. So it has to become a subset. That's what nested means. Okay. And now because of the j pi by nq, you can imagine that for that it will be nested because of this nq and 2n cube thing, because nq will become 2nq later. J will keep on increasing. So you can imagine what came as 1 pi by nq will also come as 2 pi by 2nq. So those two will be the same samples. So it will be nested. Okay. No, but their value will not be same. Their values will be same. They are supposed to be same. That's the whole point of being nested. That's what I mean, right? Same point. It's this exact same point. So think about this, right? Let me go back a little. So I was talking about this Newton course, right? I said I will divide it equally. Okay. Now suppose I make it 2x or x by 2. What will be the points?
Between 2 points.
All of this, right? So you can see these points are exactly the same. That's why they are nested. So you are reusing that. That will happen even there. So when you are going up to n cube, now think about this is the theta space. So this is up to you going up to n cube, right? So let's say this point is j pi by n cube. Now next time you are going up to 2n cube. So that means there will be a point here, but this point will still arrive because we will call it 2j by 2n cube. So the exact same point will come back and you don't need to evaluate it. So that's why it's nested. Okay. So it's the exact same point. That is the whole idea. Okay. So yeah. So this was quadrature for only 1 dimension. 2 dimension. How will you do quadrature? Any idea? You will do 1D quadrature and do a tensor product. That gives you a 2D quadrature. So Q2 is basically a tensor product of two 1D quadrature. Now that if you write in expression, it will look something like do two summations Wi Wj f at xi comma xj. Right? If it is 3, then what will happen? 3 summation, 4 summation, d dimension. What is the total number of terms you will have? N to the power d, nq to the power d, or something like that. So it grows exponentially, which means it is of no use beyond, let's say, 3 or 4 or 5 dimension. It will not scale. You can not use it. And I will show you one diagram taken from someone else actually, that how it scales when you increase, go up to 20, let's say. Okay. So nested, right? How will I not nested, and not only nested, I mean this tensor product. How does it look? Look at this diagram. X directions, think of it as CC quadrature. Y directions, think of it as CC quadrature, and then the nesting, the tensor product. This nesting is different, by the way. This is not that nesting. Think of it as tensor product. I will not use nesting. Okay. So basically, whatever point, whatever combination you can think in that 2D space that has this combination, you will take it. This diagram is showing that. 3D, you can imagine what will happen. Right? And this grows exponentially. That's the main bottleneck. You cannot use it. Okay. And for that, we have something known as the sparse grid, or known as Smolak, Smolyak, or something like that. It should be written somewhere. Yeah. Smolak quadrature. In Smolak quadrature, you do the tensor product, but you discard many of these points. It discards many of these points so that you only work with very less number of points. How does it work? You have to do the coding to understand that. I have not given it in homework 3, but I will give it in either 4 or 5. Most probably in 4 I will give it, this coding part, because this coding is important, because this is what is actually have some applicability. Okay, the Smolak quadrature. And within the Smolak quadrature, you can use the CC quadrature. That's okay. So, but it's a recursive formula. So, if you look into this formula that I have given here, it still uses tensor product, but it does it recursively. Okay, and it discards some of the points, and I will show you what points are remaining, what are not. I will not explain what, I mean, this is again anyways an adaptive thing that people came up with. So I will not discuss this equation. Rather, I will try to show you the visualization of that, because this equation you can only understand when you write a code. It's not possible that you will understand the recursion otherwise what is happening, but this visualization will help. So you see in this expression there is a L. Can you check the L? See the L? What is that L? That L is known as level, the upper limit of summation. I equal to 1 to L. That is known as summation. Label basically controls how many points there will be in one dimension. So more label means more number of points. L level does not mean L number of points, but L1 greater than L2 means at L2, L1 level you will have more number of points. That's all it means. So at level 0, you get a constant, which is shown at the middle. You see one point, a blue point, that's level 0. And you have to, it's recursive, you have to start from level 0 only. Let's go to level 1. You see 4 more points have appeared. So this is level 1. And in level 1, you can see that in x direction you have 3 points, in y direction you have 3 points. But you are not taking 9 points. Instead of taking 9 points, 3 cross 3, you are taking 5 points. So 4 points have been reduced. Level 3, how many points you are expecting? It will not be 3, 4 and 4. It will be something like this, 5 and 5. You see the green dots? The green dots are new points that has come in this level, and the previous dots remain. It's nested. So ideally, if you do tensor product, how many points would you have? 25. In this case, how many you have? 5 plus 5, 10, minus 1, 9, plus 4, 13. Right? Keep on increasing. Now, if you keep on increasing, you will see a pattern is forming. What is the pattern? That it divides the overall thing into boxes, and then it samples those boxes and keeps on dividing those. And it only samples at the center it samples very heavily, and at the corners it samples heavily. But you will not see much sample around the middle portion. You don't see much samples here. Here it's empty. If you need samples here, you have to increase the level by a very high number. And that means this method will not work if your function is actually important here. Because these are not something that is derived, that is guaranteed to work. So this will not work if your function is actually important and have high variation in that location. It will not be able to capture. But for real problem, in many cases it does work. You will not know. So luck. That's all you can do. And anyways, it will also not work in high dimension, you will see. In high dimension, let's say million or 10,000 dimension, only one method works. And that is known as Monte Carlo simulation. Now, neither subset simulation will work, nor importance sampling will work, nothing will work. Only Monte Carlo simulation works in that dimension, okay? Because that's random and that samples everywhere, and with enough sample it will work. Okay, so you will not know, so naturally it will not work for many problems. Okay, this is important. Look at the y-axis, and this is the last slide, so I could not cover polynomial chaos, but next class I'll start with that, so I want to finish this. So look at this. The top two are tensor product, and you can see how they are increasing. It is for dimension 20, I have not written it. This is dimension is 20, by the way. This is 20. So for 20 dimension, your dimension is 10 to the power 13. So clearly there is no hope. However, for these two are collocation. I mean, at a sparse grid, it is 10 to the power 3 or something like that. So it does help to a certain degree. But we are only at 20. Make it 200, it will also not work. It will be 10 to the power 10 or something like that. So the bottom line is that this is better than the others, the sparse grid one, but does not mean it is free from error. Okay. So I'll stop here. Tomorrow we'll finish polynomial chaos expansion somehow. Thank you.